this lesson, we want to go back and look at some of our basic trigonometric identities, and then also look at how we can verify some identities or use these to simplify some expressions. This will lead us into some formulas that we can use for sum and difference of functions, and then eventually lead us into solving our trigonometric functions. If you'll recall from an earlier lesson, we looked at some of our basic identities and we proved these using our definitions. And so we had our reciprocal identities, that the cosecant of theta was equal to 1 over sine theta, secant of theta is equal to 1 over cosine theta, and cotangent theta equals 1 over tangent. Now, we know that these are also true, or will work in saying that the sine of theta is equal to 1 over cosecant. But most of the time, if we're trying to simplify, we want to change cosecant to terms of sine. We like to keep things in terms of sine, cosine, and possibly tangent rather than secant, cosecant, and cotangent. So these were their basic ones, and this was a variation of it. We had our ratio identities that said the tangent of theta is equal to sine over cosine, and cotangent of theta is equal to cosine over sine. And then we had our Pythagorean identities, sine squared plus cosine squared equal 1, 1 plus tangent squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. And if you'll remember, each one of these also had variations. We could take this one and solve it for sine, and so we would get that sine squared theta equaled 1 minus cosine squared theta, and cosine squared theta would be equal to 1 minus sine squared theta. We could also, if we needed to, actually solve for sine or cosine. If we took this one and solved it for cosine, we would find that cosine theta then would equal plus or minus the square root of 1 minus sine squared theta. But again, we would more likely use this one because it doesn't deal with the radical. We could do the same thing with the other two. We could say that tangent squared theta equaled secant squared theta minus 1, or 1 equaled secant squared theta minus tangent squared theta. And cotangent squared theta equals cosecant squared theta minus 1, or cosecant squared theta minus cotangent squared theta equals 1. So they have variations. Now, if you have not memorized these identities already, then you need to memorize them now. And we will be looking at ways that we can use them. So we want to prove some identities, and we've done this before in a simpler form, but we're going to continue to do this. We want to look at some guidelines. Now, these are just guidelines. These are not rules. These are not steps. These are ideas that you can use then for proving your identity. And if you remember, what an identity was a statement that was true for all angles. No matter if you substituted in 30 degrees, 60 degrees, 20 degrees, it would be true. Now, when we get into solving our trigonometric expressions, then they will only be true for certain angles, but an identity is true for all angles. So some guidelines to use is we'll work from the more complicated side. It's easier to make something complicated easy than to make something easy complicated, although we often do. Or we can look for trigonometric substitutions involving the basic identities that may simplify things. So that would be going back to our identities, our basic rules, and using those. And so it would be looking for ways to substitute these in to make things easier. We could also look for algebraic operations such as adding fractions, the distributive property, or factoring, things like that that will help us to simplify the side that we're working on. We're only going to be working on one side. Something else that we might do is write everything in terms of sine and cosine so that we're only dealing with those two functions. They're a little bit easier to work with. And then one thing we always want to make sure of is that even though we're working with one side, we always look toward the other side to make sure that what we're doing is going to lead us toward that. You don't just start out without looking where you're going. We want to see where we're heading toward. So let's look at some identities and how we would go about proving them or verifying them. Let's take this one. Let's say we have the cosecant of theta times the tangent of theta is equal to the secant of theta. Now when we did these before, we did it by what I called the T method. We drew a line under here and then a line through the equal sign, and remember we never crossed the equal sign, we only worked with one side. Okay, one of the things we said we want to try to work with the more complicated side. Well, this side looks more complicated than secant. So let's work with this. We have cosecant times tangent. Now we didn't have any identity that dealt with cosecant, tangent, leading us towards secant. So we can't just substitute in an identity to begin with. We can't do our operations. So this is a case where we might try that idea of changing to terms of sine and cosine. The cosecant was equal to 1 over sine. And tangent is equal to sine over cosine. Well, now we can do our operation of multiplication, and we can see that the sine would cancel, and we're left with 1 over cosine. And we know that 1 over cosine is secant. Now, when you get done, the last thing you have here will be your answer. This is a case where you know what your answer is before you ever start the problem. And that's what you're working toward, is to prove that. So this one we worked by changing in terms of sine and cosine, and that's a very common thing for us to do. Okay, let's look at another one. Let's take that the cotangent of x minus 1 is equal to the cosine of x times cosecant of x minus secant of x. Now, we're only going to work on one side. And I think definitely this side looks more complicated than this side. So we want to think what we could do. And again, we don't have an identity that we can substitute in directly to these. But we do have an operation of removing parentheses. And so let's just do our basic operation. Sometimes our problem tells us what to do. We need to multiply and use our distributive property. So we would have cosine x times cosecant x minus cosine x times secant x. Now right here we could have saved ourselves one step because we know that cosine and secant are reciprocals. And so we know that cosine times secant equals 1. Now if you were in doubt on that or you forgot it, we could change secant to 1 over cosine, and then cosine times 1 over cosine is 1. But that's going to be 1. So that helps us. We wanted to lead to a minus 1, but we'd like this to be cotangent. Well, the identity we know is that cosine over sine is cotangent. So that's not what we're dealing with, but we could write these in terms of sine and cosine. This is cosine. Cosecant is 1 over sine. And so we have cosine over sine minus 1, and cosine over sine is cotangent. And again, we could have written this as cosine x times 1 over cosine x right here, and then that would be 1. So we did some of our basic operations. Now, a lot of times as I go through these, it looks like, well, this should be very easy. I've got lots of experience in this, and when I first started out on this, it wasn't easy. I would look at this and think, well, now what do I do? But always go back. Those guidelines will help you. And as I said, many of the times the one you're going to use to get started is to write it in terms of sine and cosine. So don't forget about that one. And then if you have trouble, you finally get through one, and then maybe come back later and try it again. And another thing to remember is there's not just one way of doing this. And so what you deal with is what you see. And we're not worried about how quickly we can get to the end, but do we get to the end? But there's a lot of paths that will lead us there. Okay, let's say we've got 1 minus sine to the 4th theta over 1 plus sine squared theta, and that equals cosine squared theta. Okay, this side by far looks more complicated. And I put this problem in because I wanted to remind you that we factor our trigonometric functions just like we factor our binomial functions. And so I don't want you to start trying to cancel here and say, well, sine squared goes into sine to the 4th. You can only cancel factors, and this is not written in factored form. So we would need to factor it. Well, if you notice, 1 is a perfect square, sine to the 4th is a perfect square. So this is in the form, let me just remind you, it's in the form of x squared minus y squared, the difference of squares, which factored to be x minus y times x plus y. And so we could write this then as 1 minus sine squared times 1 plus sine squared over 1 plus sine squared. We can't factor this denominator because it's not the difference of squares, and we didn't have a special factoring for the sums of squares. So we have to consider this being the whole factor. But that's nice because now we have factors of 1 plus sine squared, 1 plus sine squared, which cancel, and that leaves us with 1 minus sine squared. And if you remember from our basic identities, we had that sine squared plus cosine squared equaled 1. And remember, we said 1 minus cosine squared was sine squared. And so we can replace the 1 minus sine squared with cosine squared. So in this problem, we looked at, well, we can factor our trigonometric functions the same, we can cancel, and then we had a Pythagorean identity. So there's not just one set way to do these. You just have to look to see, well, what was I given and what can I do with it? Okay, let's look at this one. We have 1 plus sine squared is equal to cosine squared theta over 1 minus sine squared. Now this side looks more complicated, so we will work with it. And we've got a cosine squared and a 1 minus sine squared. Now our Pythagorean identities were always the squared ones. So we just talked about this. We could write cosine squared as 1 minus sine squared theta over 1 minus sine theta. Now again, we can't cancel here because this is not in factored form. These are not common factors. So again, we're in the form of x squared minus y squared. So we could factor our numerator to be 1 minus sine theta times 1 plus sine theta, which looks good because remember that's where we're heading, divided by 1 minus sine theta. Now our 1 minus sine thetas would cancel, and we're left with 1 plus sine theta. So we had to replace with a Pythagorean identity, and then we had to factor. And so again, these will not always be super simple to see. What you may want to do is to go back and write down all the ones that I've gone through and try to work them yourself, and then come back and look to see, well, what did we do, so that you can start seeing how to begin. And a lot of times the problem is you want to see the end before the beginning. And what you have to do is just start and then see where that can lead you. Let's take this one. The cosecant of beta minus sine beta is equal to cotangent beta times cosine beta. Whoops, beta. Okay, now, it may be a little bit harder to see, well, which side's more complicated. And I'm not real sure, in this case, which one is. So they look about the same. Sometimes you just have to pick one. So I'm going to start with this side. And we may come back and see, well, what would have been like if we had worked from the other side, just so that you can see that there's more than one way of doing it. And I'm going to write my cotangent in terms of sine and cosine. So cotangent was cosine over sine times cosine. And if we multiply that out, we have cosine squared beta over sine beta. Now, one of the things, and the reason I want to work from this side, is so that you can see how you begin to change a multiplication problem to a subtraction problem. And usually to do that, at some point, you're going to have to factor or distribute. So what we know here is that cosine squared is 1 minus sine squared over sine beta. Now, we're not used to distributing our division, but we can distribute division just like we do multiplication. And so I'm going to break this up into two parts because, again, I'm wanting to get it into two separate, a subtraction problem. Well, this is 1 over sine minus sine squared over sine. And 1 over sine is equal to cosecant. Oh, so it's starting to look pretty good. And here sine is a common factor, minus sine beta. So that worked out real nicely and we got it changed. Well, let's go and let's take this same problem and let's just work from the other side, which will basically be undoing what we just did. But if we had started from the other side, say we had started over here, then probably would have started by writing cosecant as 1 over sine minus sine. And now to subtract, again, your problem tells you what to do. To subtract, we have to get a common denominator, which in this case would be sine beta. So we would have 1 over sine beta minus Well, if we want this one over sine, then we have to multiply our numerator by sine also, and we would have sine squared beta. And so what we've ended up with then is 1 over sine squared beta, or 1 minus sine squared beta, over sine beta, and 1 minus sine squared is cosine squared beta over sine beta. Now you say, well, that's not where I was heading. I wanted a cotangent times cosine. Well, this, and it's good for you to see this, what this is cosine beta times cosine beta, and we only have to put the sign under one of them because it's multiplication. So I'm going to put it under here. Cosine over sine is cotangent beta times cosine beta. So again, I had to look to see, well, where was I heading? But that worked out real nicely. And so it's not always just straightforward. It's not always quick, but you keep working until you get there. And sometimes I've worked and worked, and I've just had to stop and start all over to see if I could do it a little bit better. Okay. Let's take one that looks a little complicated. Cosine x over 1 plus sine x plus 1 plus sine x over cosine x equals 2 secant x. And I think we would agree that this side is definitely more complicated. So we want to look, well, there's not an identity here that we can break it up into, or even here. So we need to stop and think, well, what does the problem tell us to do? It tells us to add. And we know to add, we have to get a common denominator. Well, we take each factor the most that it appears. So we can't factor that one any, so we'll have to have in our common denominator a factor of 1 plus sine x times cosine x. So what we look here is we've got the 1 plus sine x. We need times cosine x, so we'll multiply our numerator times cosine x, and we get cosine squared x. Well, our common denominator is 1 plus sine x times cosine x. We have the cosine x, so we've got to multiply by 1 plus sine x. Now, we can put this all over one denominator now of 1 plus sine x times cosine x. So I've got cosine squared x. Now, I'm going to multiply this out. Remember what you do there is 1 plus sine x times 1 plus sine x. And you may have wanted to have written it that way up here instead of squared. If I'd just gone ahead and written 1 plus sine x, I would have had them written there, and then I could use my distributive property. And I'm going to end up with 1 plus 2 sine x plus sine squared x when I do my distributive property. Okay, let's look at what we've got then. Well, if you look right here, you've got a cosine squared plus a sine squared. And cosine squared plus sine squared is 1. So this is 1 plus 1 would give us 2 plus 2 sine x over 1 plus sine x times cosine x. Now again, what I did was I said that the cosine squared plus sine squared is equal to 1. And so I had my 1 plus 1 plus 2 sine theta. So that gave me 2 plus 2 sine theta. Okay, now I'm looking at where I'm wanting to go. I'm wanting to end up with secant. And I know that secant is 1 over cosine. And I've got a cosine in the denominator, but I need to get rid of this 1 plus sine. It's kind of in my way. And the only way I can do that is if I can have a factor of 1 plus sine in my numerator. Well, notice I've got a common factor of 2. So I could factor out the 2 and have 1 plus sine over 1 plus sine times cosine. And so now my 1 plus sines cancel, and I have 2 over cosine, or 2 times 1 over cosine, which would give me 2 secant x. So in this one I had to do some operations. I had to get common denominators, make equivalent fractions. I had to use a Pythagorean identity right here. And I had to do some factoring. A lot of that is just algebra. Okay, let's look at this one. Cosine x over 1 plus sine x is equal to 1 minus sine x over cosine x. Now in either case, both of these look pretty complicated, or about the equally complicated. So in deciding which side we're going to work with, we could either work with either side, but I would probably work with the left-hand side because having that addition problem in the denominator is more complicated than just having cosine. We could actually break this apart if we needed to and do some things. We could have 1 over cosine minus sine over cosine. And that would come up with an answer, but it's not the one we're seeking. So I would work with this side. And in doing this, there's this will give you an idea of just another technique that you can use. The cosine's there, but I'm wanting to end up with a 1 minus sine in my numerator. And that's pretty difficult to do since I don't have anything squared. But if I took this side, and as long as I multiply both the numerator and denominator by the same thing, I can multiply by anything I want to. So I'm going to think ahead, and I'm going to multiply by 1 minus sine theta over 1 minus sine theta. That's what I wanted in my numerator. And so by multiplying both of them, then I've got it in my numerator now. So what I have is cosine x times 1 minus sine x over, and if I multiply these, notice these are conjugates. So it's going to be the first term squared minus the last term squared. If not, just use your distributive property, but I'm going to be multiplying 1 plus sine times 1 minus sine x, and I get 1 minus sine squared x, which, if you remember, is cosine squared. Cosine squared plus sine squared equals 1, so 1 minus sine squared equals cosine squared. So I have cosine x times 1 minus sine x over cosine squared Now my cosine x will cancel with one of my cosine x, and I have 1 minus sine x over cosine x. So that gives us another technique where all that we did was we multiplied both the numerator and denominator by 1. But what made me think to do that is that was what I wanted to have in my numerator. And there wasn't too many ways to get it there except to multiply both sides, both numerator and denominator by that. Now, if I had started on this side, then I would have done the same. I would have multiplied by 1 plus sine x over 1 plus sine x so that I would have that in my denominator. Okay, we want to look at this problem where we've got the sine cubed theta minus 8 divided by sine theta minus 2 is equal to sine squared theta plus 2 sine theta plus 4. And so again, I would say that the left-hand side's a little bit more complicated because of the cube. And we want to look to see what we can do with that. Well, again, we think back to algebra. We're wanting to get rid of this denominator. The only way we can do it is by factoring the numerator. And if you remember back in algebra, we had a factoring for x cubed minus y cubed. And it was what we cubed, same sign, what we cubed, times we squared the first term, we changed our sign, then it was the product of the two terms plus the last term squared. And if this were a plus, then we would have, if this were a plus, then we would have a plus here and a minus here. And so this is in that form. This is sine theta cubed minus 2 cubed. 8 is 2 cubed. So we can factor it. This would factor to be sine theta minus 2, what we cubed minus what we cubed, times, we square the first one, sine squared theta, change the sign, then it's the product of the two, so that would be 2 sine theta plus the last term squared, which is 4, over sine theta minus 2. Well, that should start looking nice because you can see where we're going is exactly the factor we have here. These factors are the same, so we can cancel them, and we end up with sine squared theta plus 2 sine theta plus 4. Okay, this gives you an idea in some of the techniques that you can use in verifying or proving identities. And there's not any one set way of doing this. This is not something I can say, do step 1, step 2, step 3. You have to look at the problem, know your identities. That's one of the biggest keys, is knowing your identities, and then just trying. And you may not always get there the first time. You may have to back up and do it again. So it just takes a lot of practice and to become where they get to be a little bit easier. But you still just have to start. Now, sometimes you may be given an expression and you're wanting to know, well, is this an identity? And on all of the ones that we've done so far, and when you're told to prove that something's an identity, then you know that it is, and you can start working toward that. But if you just had an expression, you might not know that it was an identity. So we want to look at a way that you can figure out if something is an identity. Let's say that we want to find out if the secant of beta minus 1 times the secant of beta plus 1 is equal to the tangent of beta, tangent squared beta. Now, we may configure up some of this as far as our identities go and actually know if this is an identity or not. But if we did not know if it was 1 and we didn't want to spend a lot of times trying to prove it and then find out, well, it's not an identity after all, we could use our calculator to go through and to see. Now, how we would go about doing that is we're going to graph each one of these, and then we want to see if our graph's on top. So if it's the same graph. So as we go through to graph these, let's put it in the radian mode. Okay, mine is. So let's set our window where our x is, let's see, let's set our scale between negative 2 pi and positive 2 pi. That just gives us a fairly good range. And then we could go by pi over 2, so that would be every 90 degrees. And for our y, we don't necessarily know what our altitude would be, so just to make sure we have enough, let's go from negative 4 to positive 4, and we can go by 1s. That would be fine. Okay, we're going to graph, and let's start with the left side, and we had secant. Let's just move this over here where we can see this. We had secant beta minus 1. Now, secant is the reciprocal of cosine. So we can do this one of two ways, putting it into our calculator. We can put, we're going to need parentheses. Probably what would be the easiest way at this point would just to put 1 divided by cosine theta minus 1, close parentheses, open parentheses, and if you wanted to use the secant there, we could put cosine. I'll just show you another way. Cosine x, close parentheses, and then remember we could say reciprocal. And we wanted to close the parentheses so it was the reciprocal of the whole thing, plus 1. So I wanted to put both ways so you could decide which way you wanted. And we could actually go through and we could graph that on our graph. But before we do that, let's put the other one, and that way we'll see if they're on top of each other. Well, we can go ahead and graph that one. Okay, now let's go back and let's do the second one. So let's go down to y sub 2. And we want this one to show up on our graph differently so that we'll know if it's actually on top of that. And so I was not always aware that my graph would do this, but if you will left arrow back over to this part, you can change what your graph's going to look like. And if we just keep hitting enter, notice it could be, for this graph, it could be thicker. We could actually do the less than or the greater than. And then we've got some symbols here that will show us on our graph where it actually shows it a little bit different. I wanted to go through all of those. I want to go back to, you can pick any of those last 3. This one, and then there's 2 more after this, but this shows how it's going to lead into the graph. So then we're going to go right arrow over here, and we're going to put tangent x, close our parentheses, and then we'll say squared. Remember, that squared means that we're squaring the whole function as we go through here. So now we'll put our graph. And you can see where that one's actually graphing. So you can see that it does go right on top of that. If it weren't for that, we wouldn't even be seeing anything happen. And so that's why it's nice to have uh, the graphs done two different ways, because if we hadn't done that, we wouldn't see what that graph was. And let's just go back and I'll show you what I mean there. If I go back to the y, that y sub 2, and we go back out here, and I go through and I change it to be the original, which is what that one was. I went too far. Okay, then I graph. Okay, there's the first one. And now you can't even see, you know that it's still working because of that little line that was up here, but you never saw anything. And so it's hard to know then, well, what was that second one doing? About all that you could do then would be, say, to trace and to move your cursor along the line, and then every once in a while switch. That shows you that, well, that it's on there for that function, and then it's actually on there for the second function. And then you could move your cursor, again to where it came over on one of these others. And then you could switch to the different one and see. But that gives you a way to see both graphs. Okay, let's try one more of these. And this just gives you a way to know then if you've got graphs that are identities. And as I said, most of these that are the ones when you're told to prove that they are, then we know that they are identities. Okay, let's say that we've got okay, let's take this one. Secant x minus cosecant x equals cosine x minus sine x over cosine x times sine x. And we want to know, is this an identity? We don't know, so we want to start out. So let's take the first one, and we want secant, which is cosine x, close parentheses, reciprocal, minus cosecant, which is sine x, close parentheses, reciprocal. So that gives us our first graph, and we could go through and graph that. Some of these have kind of neat looking graphs. Okay, now let's take our second one, y sub 2, and we're going to go down to y sub 2, and while I'm thinking about it, I'm going to go back and change how that will graph so that I can tell the difference if these are actually the same graph. Now here I have a numerator and a denominator, so I'm going to need my numerator in parentheses, and I'll need my denominator in parentheses. So I've got parentheses, cosine x minus sine x. I have to close my angle, then close my numerator, divided by parentheses, cosine x times sine x. Close my angle, close my parentheses. And now I'll press graph. Okay, and I can see that it's coming down and it's not graphing right on top of the other one. So these are not the same graphs. This is not an identity, and there is no way that we could work like we did the previous problems and make one side be the other side because they're not identities. These are not true for all values of x. And so when you don't know if things are identities, then this is a quick way of finding that out and before you spend your time trying to solve. Most of the time you're going to be told that things are identities and you're going to be proving them. So the things that you need to know then are your basic identities. These are true for all angles. And then have some guidelines about how you would go about proving your identities. Work from the more complicated side. Look for trigonometric substitutions. Look for algebraic operations that you can do, especially your distributive property and factoring and adding your fractions. Write everything in terms of sine and cosine. And then to remember always to look toward the side that you're working toward. But most of all, it takes practice.